Hello, this is Pat Spoden with the National Weather Service office in Paducah. I just wanted to give you a little update on some of the changes that have been going on in the office over the past year or two, and some that will be coming to the office in the next year or so. It's important to note that this information is representative of my thoughts, not necessarily those of the National Weather Service. One of the changes that's occurring is the way that we forecast. For many, many years, we'd focus in on, say, with the GFS or the ECMWS, which is the European, or the NAM solution says, and we'll try and see if two of these models can agree, and that's where we'll go with our forecast. And at a sidebar, the GFS is going to 13-kilometer resolution soon. But in reality, what's happening is that the focus is moving towards an ensemble approach to forecasting. An ensemble is or are groups of model solutions to come up with the most likely scenario. So that's one way we look at ensembles. We can also look at ensembles looking at similar weather conditions over the past 30 to 35 years, or what we call analogs, and comparing what happened then and can we use that then as a forecast over the next several days. We also look at comparing it to normal. What in the forecast is way out of whack? What's way out of what should happen for this time of year? What's against climatology? When there's a big break between what you see and climatology, there's a good indication that this could be a relatively significant event. So here's some ensemble data output. This is from Penn State University, available on the internet. And you can see on the top picture, there's a lot of lines. Each line represents a particular model height from a particular model. So when they're all in agreement, the lines are fairly close together. When the models are having difficulty as location or placement, then you end up with something like this that's occurring up in central Canada. Well, let's look at the average of these, a consensus forecast. So if you take all these together and you add more heights to it, this is what you come up with. And you can also see where the heights are well above normal for this time of year or below normal for this time of year. And so when you start seeing 2 and 3 standard deviation differences, that's fairly significant and something that you need to pay attention to. Now, what if we look at standardized anomalies versus what it should have been? Or here we're looking at the NAIFS. The NAIFS is a North American ensemble forecasting system, so it's a combination of members from the Canadian and the United States models put together. So here we're looking at mean temperatures and standardized anomalies for Friday, November 14th, a forecast made many days ago. And what it's showing is at 850, which is about 5,000 feet up, and even at the surface, down in Texas and down in the south, we're looking at much below normal temperatures than what should be happening for this time of year. And of course, this was in the middle of the cold snap that we had. And so these models were picking up on that pretty well. Well, what if we look at what we call reforecasted precipitation? And here is a forecast from November 6th for 120 to 240 hours out. So basically 6 to 10 days from November 6th. And it's saying, well, what happened in the past is that we ended up with this kind of rain. And so can we use that information to say, well, we'll get maybe 1/10 to 2/10 of an inch of rain in our area during that time frame? Would that work out for our current scenario? We can do the same thing with severe weather. Going to the SIPS website from St. Louis University. Here they've been able to track using the GFS on November 7th, looking out 96 hours. So forecast on 0Z on the 11th, so 6 p.m. on the 10th approximately. Said in the past, if you put together all those patterns that look similar to what they did from the model that was run on the 7th of November, this is what happened. there were some severe weather. There was some severe weather. There were a few tornadoes and hail and wind reports. Now, that doesn't mean that we're going to see that, but it opens you up to that possibility. If things happen to move in the way that this one particular model's going, maybe it's something that we need to be concerned about. So we can take all these ensembles together, and even though this doesn't take all of them, it takes in a large chunk of them. And from that, we can get a relative mean of predictability, meaning that when we're seeing 90% here off the West Coast and up into Canada, you see a lot of orange with these heights, and there's a big ridge out there. Well, there's basically 90% certainly that you're going to reach those values, and the ridge is going to be located over this area. And of course, generally when it's warm over Western Canada and parts of Alaska, it's colder over here. And so we're very confident this ridge is here. We may not be quite as confident as to the location of this particular trough or how deep it might be. So those are some of the ways that we're using ensembles to look at not only groups of forecast members, but also groups of information from the past and comparing it to the current. Other changes that have been going on in this ensemble type thought process. We're using a system now where we are blending models together locally, and it looks at local solutions to these models and even puts together what we call bias corrected data, where it looks at how far has this particular model been off over the past few weeks? And if it's been cold, then we're going to drop these temperatures down. If it's been too warm, we're going to raise the temperatures up. But basically, what the forecasters have in front of them now is about 43 different types of guidance in the first 24 hours, each one giving them a forecast. And we could take these and we can blend them together and make things that we might call a super blend or an all blend. And it can give us some values. And then the forecaster's job is to go in there and do we need to tweak that and adjust to it. So here we're looking at, again, 43 different types. And if you're looking at just the initial model raw output, it's always interesting to see that, a lot of times the GFS and the NAM and even the Canadian models are actually down on the lower end. It means that when we're taking the data that they give us and then we're adjusting it, we end up with better forecasts. We also do this out to day 7, and we use what we call super blend. For 2 times a day, generally about a little after midnight, a little after noon, we take in 40% of cons-all, which is basically averaging everything together. Then we take 25% of the bias corrected averages, 15% of the best 3 models that work in our area over the past couple weeks, 10% from the Weather Prediction Center, the National Prediction Center, and 10% of the previous forecast. And so super blend then can generally give us a better value than what the individual models say. It's not always the case, but most of the time it's what we start with. Well, we always start with it, and then we adjust from there. This is where we take that ensemble data, and when we're looking at things that are 2 and 3 standard deviations off from normal, then we can come into the super blend and make some adjustments to that, saying that, this isn't quite working the way that we want it to, make those adjustments. And so we're basically moving towards a consensus approach here and in the short term. And don't be surprised, in the next few years, you'll start seeing the Weather Service go out to 10 days on our forecasts. Shifting gears a little bit, AWIPS 2. It's a new forecast system that's going to be installed on February 4th. Not a whole lot of change for the forecasters, but internally there's lots of changes that is going to allow us to make more changes in the future and give you more information to help you with your decision making. One of the neat things that's coming out, it'll start moving into our office in February, right after we get AWIPS 2. It's called multi-radar, multi-sensor. It's important to know this is not your grandma's mosaic. This is not like the mosaic that you see on the internet or on your cell phone, or even what we see in our computer systems now. But it's a mosaic of what we call voxels, or volume pixels. So there's the new word that you can throw out to your friends and impress them, voxel. And it updates every 2 minutes. And basically it combines all the information from nearby radars and gives us information that's really going to help, and in some cases simplify some of our warning decisions, make it a little bit more straightforward by giving us the direct information we need, rather than right now we're trying to currently search this information out. So there's products like, we can't get now, reflectivity on the -20 surface. Well, why do we want to know that? Well, if we know what the reflectivity is up there, you're real close or in the main hail growth region. It also helps us to assess the updraft strength and severe potential. The stronger the updraft, the more likely you're going to have severe weather. Many of you have heard of VIL, vertically integrated liquid. Well, this stream of products has something called vertically integrated ice. And what that helps you see is the strength of the updraft, because the strong updraft is pushing that ice way up there, and the radar can determine what's ice and what's not. And so it really points out where the stronger updrafts are before you're going to see it on your typical reflectivity screens. Other products like Mesh, it's an improved hail size algorithm, Azimuthal shear, where we can look at areas of shear or areas of rotation. So here's an example of MRMS data. Here's where you combine all the radars and you look at the lowest altitude from any one radar. You've got a series of strong storms here over the Dakotas. Now, if we look at what's the reflectivity at 0 degrees, it's a little bit easier to pick out the stronger storms. This might be a little bit more useful when we're in the winter time and looking for where's the freezing level, what's the reflectivity there. We can look at -10 degrees C, and here we are at -20, and right away you can say, well, out of all these storms down here, these are the strongest ones, and maybe these are the ones that I need to interrogate more. Now, that doesn't work in every situation. It works pretty well when you're in the warm season. In the cool season, we're going to have to see, because a lot of things occur at the low levels in the cool season. Here's another example of MRMS data. Here we're looking at data from the Tulsa radar, and it looks like there may be one, potentially two different circulations in there, kind of hard to see. Whereas the MRMS data says, yes, there are two circulations in there. So you really need to go and interrogate this closely the best that you can. Most of you know that when we're in certain volume coverage patterns, we're getting sales data, which means you get an additional 0.5 slice about once every 2 minutes now, depending upon what we're looking at. And in the future, I would just expect that to increase maybe once every 1 to 2 minutes. It might take a little while for this to occur, but I think we'll be seeing more radar data in the future. So that's just a quick update of things that are going on. I hope you enjoyed it. Thank you.